3, 2, 1, 0.
Hello everyone, I'm your host Bhumika, here with a new video and an interesting concept. It has been a virtual world, so I've decided to share a little bit amount of information with you all through this medium. And I'm here up with a new concept, which is the Aditya L1 mission, India's first dedicated space mission to study our nearest star called Sun. And I'm pretty sure that you will get something more than interesting as we move on further. So before moving directly to the mission Aditya L1, we are supposed to know that why we need to study the star called Sun. You look at the Sun in the day sky and it generally looks like a flat bright star. But in reality, it is a very dynamic star and is always changing. It changes in the order of seconds, minutes, hours, days, weeks, or even centuries. So different kind of variabilities is seen in the Sun. And as you can imagine, if you want to study these different variabilities, you will need different descriptions and different kinds of physics to understand it. The other question which arises is, are these variabilities affecting us, our life, or our atmosphere? The answer is yes, it is because of the presence of Sun at a particular distance away from us. So Aditya L1 mission is a spacecraft mission to study the Sun, of course, and it has been designed and will be built in collaboration between the Indian Space Research Organization and various other Indian research institutes such as the Indian Institute of Astrophysics, the Pune Physical Laboratory, Ahmedabad, Udaipur, then ITPHU, TIFR, different ISRs. So it is a fully Make in India project which is full to and 100% funded by the ISRO. It is a 100% ISRO project, and it was about to launch in 2020, but due to this COVID-19 and other ambitious projects such as Gaganyaan, it is unclear when ISRO will launch this Aditya L1 mission, but most probably it will be in the wake of 2022. So I must say that it is a very fortunate opportunity for all of us, and we are entering into a golden era of solar physics in India, I must say. This Aditya L1 is a 1500 kg class satellite carrying 7 payloads. These 7 payloads will cover up Sun's photosphere, the UV, the soft and the hard X-rays, the chromosphere, and the visible or the outer atmosphere of the Sun, which is called as the solar corona. Yes, incidentally, this name of the virus has been named after the Sun only, which is the corona. So when there is a total solar eclipse, we are unable to see this corona. This is because of the emission coming out from it is very weak as compared to the solar disk. So if we want to see this corona, we have to go to the outer space and we have to look at a shorter wavelength, then only we will be able to see the corona. And this is what the Aditya L1 will be carrying out, the task of coronagraphy. Earlier, this Aditya L1 mission was only Aditya 1 mission, not L1, and was conceived as a 400 kg class satellite carrying only one payload, which was VELC, Visible Emission Line Coronagraphy, and was about to launch in an 800 km lower Earth orbit. It was only Aditya 1 mission and not L1. Now this new Aditya L1 mission is Aditya Lagrangian 1. Lagrangian 1 means, now there is a term called as Lagrange point, which is a region of space that lies in the pathway between the Earth and the Sun, where the gravitational force or the pull of both the bodies is balanced, that is in equilibrium. The European Space Agency explains that any spacecraft in the orbit around the points will simply hover without the influence of any gravitational pull. This makes it possible to place the objects in the 3D orbit around these points, which is known as the halo orbit, as you can see in the picture. Majorly, there are 5 Lagrangian points. It has advantage of viewing the Sun without any accumulations or eclipses. And yes, you are guessing it very correct that therefore this Aditya 1 mission was revised to Aditya L1 mission and will be inserted in a halo orbit around this Lagrangian point 1, which is 1.5 million kilometers away from Earth. So there are 7 payloads as I've mentioned earlier. The biggest one is this coronagraph to study the different parameters of the plasma in solar corona and to study the dynamics and the origin of this mass ejection. It has 4 cameras to look at just not imaging but also spectroscopy. Spectroscopy allows to diagnose some of the parameters of plasma like what is the density, what is the temperature, the velocity it is moving in the interplanetary medium and so on. So it is a very comprehensive instrument which has possibility of looking at imaging and spectroscopy both. The major attempt this mission will carry on is the oceanography, which we didn't had earlier. Then the second major payload is SOOT, Solar Ultraviolet Imaging Telescope, which will be looking at some of the images of lower and middle layer of solar atmosphere. And SOOT images will be very similar, of course. SOOT will not look at a corona but will look at a chromosphere and primarily the photosphere. It will be looking at between 200 to 400 nanometers of wavelength. And why ISRO chose these kind of wavelength is that NASA and other already had a lot of UV and X-ray imaging devices, but this near UV domain regular observation was not there, that's why. Then when we are actually going to a place called Lagrangian point 1, which is in between the sun and the earth, essentially we are going towards the sun about 1,27,000 kilometers. This is about 1% of the distance between the sun and earth. So the ideal thing is we can look at a sun and continuously take some images through some instruments which is looking directly to it, which is called as remote sensing. There is also a possibility which is in situ observation, that is if you have a detector and some particle comes, so it will record that what kind of particle it is and what are different energies and what are the different ionization states of that particle. And if those particles have a magnetic field, then these are called as in situ instrument, just sitting there. So what it has is combination of 4 remote sensing and 3 in situ instruments, altogether 7 instruments. So this Aditya Solar Wind Particle Instrument Aspects is such an in situ instrument which will be looking at the solar wind properties, because solar wind contains all these particles which are coming from the sun. Then this is a bit complicated part. What it is showing is the coronal mass ejection. If you want to study the properties of coronal mass ejection as it travels close to the sun into the interplanetary space, how it gets propagated, does it get accelerated, decelerated, or does it get moved with the uniform velocity? So to do all that you will need observations from different coronagraph. So this is a height time plot, the first graph as you can see in the picture, and the origin is the sun. From this graph is that we can see that there are hardly any observational data point very close to the sun. In the second one, the next graph we have is our theoretical value or model which we think are right for describing the propagation of CME. Here the velocity is small, then it goes high and then it saturates. The third one, what it means is that initially there's acceleration, then probably the CMES flows down a bit when it travels 5 to 6 solar radii and then eventually it travels with the solar wind. We did not have any data points in these regions, so Aditya is gonna focus on these regions, and which will allow the humans to understand the properties of propagation of CMES, because only then we will be able to predict at what time it will come. The other one is PAPA, the plasma analysis package for Aditya. This will be looking at a different energy ranges, that is 10 electron volt to 3 kilo electron volt as compared to the aspects. So these complement each other and its function is to understand the composition of the solar wind and and its energy distribution. Then we have the 2 X-ray spectrometer, which is going to look at a sun as a star. So it will look at a total flux coming out from the sun and will record that with 2 energy bands, one which is at 1 to 30 kilo electron volt, and for very high energy we have the other instrument called as ARIES, which is going to look at 10 to 150 kilo electron volt. The combination of these two will allow us to study these flares of different sizes and different scales. Hence it is very difficult for one instrument to study and detect, characterize all these different sizes of the flare. So for that, 2 instruments of X-ray spectrometer will be used, which is the SOLEX and the HALOS. And the last one is the Fluxgate digital magnetometer, which is going to measure the magnitude and the nature of the interplanetary magnetic field. So as I said, it is going to sit there, and if some CMES is coming from the sun, it will pass through the Lagrangian point 1. It will hit the magnetometer, and then it will immediately detect that what is the extra magnetic field. So CMES is like a magnetic cloud, which will help us to understand the properties of magnetic cloud and so on. Thanks for watching me so patiently, and also don't forget to like, share and subscribe, and write down all your queries, question, your ideas in the comment section. All those will be answered surely. Till then, stay tuned. Shush!